Yeah? Yeah? Hi. We're Chef, and we had big news, and so this is the big news. I want to talk for a second about Chef, the company, and our vision for what it's possible to be. We at Chef want the most enduring and transformative companies in the world to use Chef to become fast, efficient, innovative, software-driven organizations. And that's been our mission for years now. And it's bigger than Chef, it's bigger than software. It's really about how do we help all of these companies really figure out how to transition into the next version of the economy. And we've been doing it for about 8 years, and we've had the opportunity to see thousands of different customers across every industry, across every stage, from small startups to giant big web companies to retail, video games, insurance, airlines, all these different companies, tons of different situations in every possible piece of the spectrum. And what we've learned is every single one of them, without question, if they want to become the most fast, efficient, software-driven organizations in the world, it starts with their human beings. It starts with the people who work there. And it starts with the way that those people work and the way that they relate to each other and the technology they use to get their job done every day. And if we can get that right, how they work together and the technology they use that reinforces those behaviors, then those people have a shot at building really great products that other people will love. And if you build great products that other people love, then you have a shot at being a company that people love and that they'll keep loving and that they'll sustain your business and those people for years to come. And so if we need to change how those people work, if we need to change how they work together, you have to do two things at the same time. You have to change the culture of how they work, and you also have to change the technology by which they do their work. So a good example here is the workflow, right? If you listen to me or somebody else talk about DevOps, right? And it's really easy to hear what we say and be like, yeah, that sounds way better than what I'm doing right now. But if you just try doing it, but you don't change anything about the way your workflow works day in, day out, it's going to be really hard to do DevOps because your whole technology, the entire way you work every day when you go to work, just fights against you. And eventually you'll stop and be like, man, this DevOps thing is BS, right? I don't want to do this. And really, when we talk about what the technology challenge is, and the people challenge too, there's no difference really. If we want these companies to be fast, innovative, and transformative, what we have to do is optimize the way that they build applications, the way they deploy them into production, and the way they manage them throughout that lifecycle. And that's really the challenge. And it's not just Chef that's trying to do this. This is if you build infrastructure or you build automation, this is the central challenge of this generation of technology. Can we get all the companies in the world to be as fast and efficient and innovative as Facebook, as Google, right? And when we set out as an industry to solve this problem, we tend to do it from two different perspectives. Either we do it from the perspective of the enterprise, or we do it from the perspective of the big web. If we do it from the perspective of the enterprise, what we start out with is an image that sort of looks like this, right? You have all this infrastructure that's accumulated. You know, GE is a good example. GE has existed since Thomas Edison. So that's a lot of infrastructure, right? And you didn't have a lot of choices about what those things were. And so you've got different hardware providers, you have virtualization, different virtualization people, you've got multiple clouds and IaaS, you have lots of operating systems you run, and then on the top you have this emerging runtime layer where you have like grid technology like Mesosphere and Kubernetes, and you have PaaS providers like Cloud Foundry and OpenShift, and you have containers in Discovery where you're just like using Docker and doing etcd and console, and it feels great. And then all that stuff sort of builds up and crosses these silos that we all know, live, and love so much inside of the enterprise. So when you think about how that software moves at the cultural level through its life, you know, it starts out maybe with some like vision of what the product should be, although often I don't know that there is one, but hopefully, right? And then it goes to some software developers and they write some stuff, and then it goes to QA, and then it goes to operations, and then it goes to security, and it sort of bounces around through that whole life cycle. And the truth is, if you sit down with this as your point of view to try to design a solution to that build, deploy, and manage problem, two things happen. One is you have a tendency to design your technology for a single silo because it's really hard to break across those silos, right? So we tend to build technology that does application deployment. We tend to build technology that does configuration management. We build technology that does security and vulnerability. Like each silo gets their own little piece of technology, and they get to buy it and do the thing that they do. And that's great. But fundamentally, if we're trying to fix the bigger build, deploy, and manage problem, the scope isn't big enough. We can't fix it from just one silo's perspective. We have to think about all the different perspectives of everything in the silo. So every once in a while, you're brave enough to pop up. And people are like, hey man, we're going to fix the entire build, deploy, manage cycle across the entirety of the enterprise. It's going to be amazing. And what they tend to do is you have to go take a bunch of tools and string them together with a bunch of glue to try to build this thing that manages the build, deploy, manage cycle. But when you do it, you're forced to integrate to all the choices that every silo made across the chain. And the side effect is the way it feels to use is like a crazy glued together Rube Goldberg machine, because it's a crazy glued together Rube Goldberg machine, right? And that need to force to integrate, that's one of the things that causes the products in this space to just feel wrong, because they are. Because they weren't actually designed to solve your problem. They were designed to solve this huge generic problem that talks about how it integrates with all the possible choices and all these things. And so the products, they just feel like soup, and they're not very compelling. And so it's easy to turn to the big web and be like, all right, these guys got it, right? They build, deploy, manage software super fast. So let's do that. And it's true, you're right, they do. And the difference between them and the enterprise is really that they started out thinking about platforms from the beginning. They have a single infrastructure platform that they build on. They have a runtime layer that sort of sits on top of that mitigates your access to like individual compute resources and storage. And then they have operations teams who are responsible for managing and running both of those layers and interacting with software developers who write applications to deploy on top of those runtimes. And it all works together and goes pretty fast, right? And there's fewer silos, and they can ship software, and you get Facebook and Amazon and Google and Twitter and all of those companies. And it's amazing. And so it's easy to sit down and be like, great, what we should do is just design a solution from the big web's point of view. We should just do it like they do it, and it'll all work out. But when we design from that point of view to try to solve the build, deploy, manage problem, we get two more problems. So one is, each of those companies was different from each other. But what they had in common was that they controlled the application from the day they were born. Facebook is Facebook because they wrote Facebook. Google is Google because they wrote Google. LinkedIn is LinkedIn because they wrote LinkedIn. I can keep going. But that's different than the enterprise, right? If I'm a company that's existed since Thomas Edison, as an example, I don't have control over the application, right? Sometimes I do, but often I don't. Banks often didn't write the core banking software that runs the bank. They bought it because banking has been around for a super long time. And so when we think about how those platforms came together and those choices they made about a single infrastructure and a runtime that's holistic and the way they write applications on top of it, that control over the application is a fundamental difference between how they work and how the rest of us work. And the second thing is, for all those companies, the platform itself became the point. The product that they sell you is the platform. What is Google without the massive infrastructure that enables Google search, right? That ability to do that is what they are. Whereas in a lot of cases, we sell physical things. My first job was working in a comic book store. I sold comic books. I can imagine a world with digital comic books. They already exist. You can go use Comixology. But the platform that Comixology runs on, not necessarily the product, right? The comic books are the product. And that's the point. It's a little different. And so when we design just from this point of view, what we tend to want to do is rewrite the world, right? We say, if it's going to work, we have to just take all the software that's ever been written, and we need to rewrite it toward a platform that, so far, we've never had a generic one that works well enough to be able to write all the software too, right? So it doesn't mean it's impossible, but it's complicated, and it's going to take a long time. And so we asked ourselves, is that how it has to be? Do we have to design for this build, deploy, management problem from one of those perspectives? What would happen if we did both? What would happen if we just said, how exactly is it that our applications should behave throughout that build, deploy, and management cycle? What are all the things that they should do? And let's try to build something that makes that easy. And we're really proud of the answer, which we call Habitat. Yay! If there's one thing I can impart on the live stream, it's okay to clap for yourself. Habitat is what we call application automation. And what we mean by that is, instead of thinking about those problems from the perspective of the infrastructure, what we say is, everything about the application's behavior belongs to the application. It should be about the app, right? And so when you think about its point of view, when you design for that build, deploy, manage cycle, everything that the application needs to live at that layer. And it's different than saying it's about the infrastructure. So when it's about the infrastructure, we build all this code and we try to build up toward the application, and then we try to like bang the application into place. And instead, Habitat says, nope, it starts with the application. Everything that the application needs to do lives with the application. And that sort of leads us to what the big aha moment was for Habitat, which is this. The automation has to travel with the application itself. So if the application needs to do something in that build, deploy, and management lifecycle, it's the application's responsibility to do it. And we need to get it without having to deploy anything. And if at any point we have to actually go and do something other than just deploy the app, then we've sort of missed it, right? That build, deploy, management cycle isn't complete. And one great side effect of this that we noticed as we built Habitat was that we started to feel like we were avoiding what we call the production cliff. And so if you've ever built any infrastructure or any automation, this is a story that probably will resonate. Basically, you get a new technology. Feels great. You start using it in dev on your laptop. It feels amazing. You're like, this is it. This is going to change everything, right? And so you start using it more. It gets a little more complicated. And then you get to what I call the peak of false hope. And the peak of false hope is that moment where you see the potential of the technology, but you have yet to actually get to any of the problems you'll encounter as you get closer to production. And so there's this great moment where you crest the peak of false hope, and it looks like it's all downhill from here, right? And you're like, oh, it's going to be great. I'm going to roll it out everywhere. It's going to save the day. My whole life's better. It's going to be one button. Everything's going to be the best. And then you hit this like weird curve that just shoots into the stratosphere in difficulty. And that's the production cliff. And so far, in my experience, that's happened for every single piece of infrastructure and automation software I have ever used, except for Habitat. It feels so far like we've been able to hold that line where the difficulty of moving that software from left to right as it gets closer to production actually doesn't increase all that much. So let's show you rather than talking about it. So everything in Habitat starts out with a plan. And plans are written in the native language of the platform, and they're as simple as we could make them. So one thing that we really realized was there's lots of software in the world, and when people, especially open source software, and people talk about that software in the language of the platform. They write a shell script, or they tell you what commands to run to compile it. And we really wanted to keep it as close to that as we could. So we wanted the abstraction to be minimal. Every package, every plan in Habitat has a name. So we're going to use Redis. Redis is an in-memory database for data structures. And we're going to just sort of use that throughout the demo. So software in Habitat also has an origin. That's the place the software comes from, right? So this particular plan comes from Core. Core is the Habitat project itself. However, you can imagine a world where like Microsoft Word, right? So what would be the name of Word? It would be Word. And then the origin would be Microsoft, right? And then the software has a version, so we can know like which one I'm running, right? And then we have this really low abstraction declarative way of saying, hey, this is the license for the software, this is who maintains it, this is how we can validate that that source is exactly what we thought it was and how we go get the software. We also specify all of the complete dependencies of the software. And so here, Redis has two. So it has two build time dependencies. It needs make and GCC. And then at runtime, it just needs glibc. It actually has no dependencies at all, except for the C library that the platform needs. And then we declare that this package contains a service, right? And in this case, that service is Redis, right? And that it runs on a port 6379. And the plan files can do more than this. So throughout that entire build lifecycle, you have these simple functions that plug in at each stage of the process. And so most software in Linux, you build it by saying configure, make install. Redis doesn't have a configure script, right? And so we've overridden the typical process to say just run make. Don't worry about configure. OK, so we want to build Redis, right? So the first thing we have to do is set up Habitat. So we're going to run a command here called hab setup. So the first thing it prompts me to do is create an origin. So like I said, software comes from somewhere. And since I'm just building this software for myself, I'm going to build an origin for me. I'm just going to call it Adam. So I'm going to say, yes, I want an origin. I'm going to call my origin Adam. And then the next question it asks is if you want to enable analytics. So one of the things we take really seriously in Habitat is that production cliff problem, right? We really want to know if the software is working and if you're having trouble. And so we've put in a bunch of anonymized analytics that you can opt into that will tell us if you're having trouble. If you're sketched out by analytics or whatever, just say no. Everything's cool. But that's helpful. So we're going to opt in because, hey, I trust myself. OK, so now we're all set up and we're ready to go. So we're going to go and build ourselves a plan. So plans get built in what we call a studio. So a studio is a clean room environment that takes that plan and that list of dependencies and puts them together and builds the software in a way that's safe and fast. So let's do that now. So I'm going to say, I happen to have the software for that plan in a directory. It's called Redis, right? And you can see that plan.sh right there. That's the plan file that I showed you earlier. So we're just going to run hab package build Redis. OK, so the first thing it did was import my origin key, right? So that's that secret key that we're going to use to sign the package later. So everything that happens in Habitat is safe by default. And that includes that the packages are all signed from their origin. So you can attest that that it came from me, right? OK, so what it's doing now is installing all the dependencies it needs to build. And in a minute, it's going to go download Redis, compile it, and stick it in an artifact. But while that's happening, we're just going to move on for a second, and then we'll come back. So I want to talk more about what's inside that plan directory. So one of the things that's in there is the configuration options that need to travel with the application. So in Habitat, the automation travels with the app, right? And so that means anything that a user could change about the application, we need to be able to say and have be in the application itself. And so one of the goals was that it should be really easy. And so we chose a format called TOML. What's great about TOML is that it looks like an INI file, which basically we've all been writing since the 80s, right? It's like a key and a value, and there's like an equal sign, and everything's cool. It also supports comments, which seems like a weird thing to call out in a presentation, but the truth is a lot of our configuration file formats right now don't. And you really need to be able to annotate what it is that's inside this thing, right? It supports complicated data structures if you need them. So at the basic level, it's basic. But some software, you can think about like web servers, Apache or Nginx, they need more complicated data structures to be able to really talk about all the things they could possibly do. You need hashes and arrays. And TOML gives you that with a simple, easy syntax. So it scales up really well. Most software wasn't written for Habitat. I think the only software so far that was written for Habitat is Habitat. You need to be able to translate from that configuration language we give you in TOML to the natural configuration language of your application. So this is a little snippet of the Redis configuration file. And it's just a simple template, right? Anybody who's used modern web technologies this should look familiar to you. We chose a very minimal approach. So one of the things I'm going to talk about later is that the data is the API. But essentially, you don't have any logic really in these templates beyond the basics. You do substitution. So if you want to change the port, you can set a value called port, and then we can put it here in the template. We can do branching and looping and basic conditionals, and that's really it. There's no functions that you can't assign new data, right? It's pretty straightforward. One beautiful thing about it is you can document what's available. And so it's pretty easy to reason about what you can put inside these files. So another thing that the plan can do for you is it can let you specify lifecycle hooks. So when you think about the lifecycle of a running service, right, it starts itself, then it's running, it might have to reconfigure itself, it has health checks and status. All those things in Habitat are just hooks that also get passed through that same templating layer. So they allow you to customize the behavior of how your service is going to run. Some examples there, like I said, initialization, runtime, health checks, right? So you need to have a standard way to say if the application's working or not. This matters later for deployment, right? All those things are just lifecycle hooks. And as we discover more, we just add more hooks into Habitat, and now that piece of the lifecycle is instrumented as well. OK, let's go check in on our build and see if it's done. Hey, look, it is. So what we see here is that, in fact, we have built ourselves an artifact, right? So if we scroll up, you'll see that we had compiled Redis here, right? And then we'd created an artifact. We created some checksums, so we can actually validate that all the files that were put inside of the artifact are still there. So later on, you can come around and make sure that nothing's tampered with it on disk. So these packages on disk, I'll talk about in a minute, they're immutable, which matters. We signed our artifact with my key, right? We also signed the hash with my key. And then, I'm using the mouse backwards. We also generated an artifact. So in Habitat, artifacts have this .heart extension, right? So we have this heart file here that we can go and install. So let's go ahead and do that. So I'm just going to grab this here. Oh, no, this way. OK, so once we have an artifact, you need to store them somewhere so that you can install them somewhere else, right? So it's cool you built an artifact, but now it has to go up into what we call a depot. So a depot is the central location where all your artifacts live, right? And we have a publicly hosted one that you can go to, and you can create yourself an origin, and you can upload your own packages. And I'm going to do that now. So I'm going to take that artifact we just built, and I'm going to upload it to our public depot. So I'm going to do hab package upload. Boop. OK, so now what happened was I took that artifact I built, and I uploaded it to the central depot. And we can go ahead and use that artifact. So when we want to install it, you might notice a pattern. Everything comes up through this hab command, right? So there's this simple, easy pattern for the way that you interact with Habitat, which is you just say hab and then the thing you want, and then Habitat does it for you. So let's install the artifact we just built. So we'll say hab package install Atom Redis. Bloop. And now that package exists, and it's installed on this box. So one thing you might notice is that when we created the package, it has this style that says Atom Redis 307 2016 and then like a timestamp. So that's the origin, comes from me, the name, Redis, the version, 307, and also a release number, right? And so that release number is what allows you to have different configuration options for the same version of the software, because sometimes the software didn't change, just your configuration did. And so we can actually use that specificity to be more clear about which package to install. So it's already here, but we can do this. And now we would install that specific version with those specific set of dependencies. So if you remember that we included all our deps, what that lets us do later on is be sure that this version of Redis has only the things it needs to run. OK, let's do that. Let's just look at how that stuff works. So we'll do hab package install Atom Redis again. So everything that Habitat does lives in this /hab directory on your box. And we did this because Habitat packages can run anywhere. They can run in containers. They can run in on bare metal operating systems. And we just want to be unobtrusive to what other systems have done. So let's go look at where that package is. So if we go to hab packages Atom Redis 307, right? We can see that we got this directory that's full of stuff. And in here are the binaries themselves, right? So that's Redis that we compiled. It also has the metadata about what we built. So a good example there is this is the list of transitive dependencies. So this is all the dependencies that this software needs to run in production, right? And that's it. It just needs glibc and a little bit of the Linux headers for some sauce. It also tracks, though, your transitive build dependencies. So we can also tell you all the software that was used to compile the software. Like I can tell you the specific version of GCC. I can tell you the specific version of libgmp. And so there's a whole class of bugs that are very rare, but are hard to track down, where they came from a library that you used at build time, not at runtime. So how do you even know when those bugs occur? And with Habitat, it's really easy. We can just ask the metadata about what's there. So the other side effect is that Habitat packages link directly to the specific release of the software. So this is going to get a little nerdy, but for those of you who understand dynamic linking, let's just do this real fast. So this is the Redis server binary we built. And the thing to notice is that on the right-hand side of that little fat arrow, you have things that point to those hab packages directories. And what that means is if we were to launch a new version of Redis that linked against a new version of glibc, we could actually install those two things side by side on the same box. And that's the way that you can actually safely deploy new versions of your software, right? So if you think about it, we're freeing you up from all of that weird unsafety edge conditions that happen when you run software in production. So one side effect of having all those glorious dependencies is that it's really easy to repackage Habitat artifacts into any other format. So everybody loves Docker. I love Docker. The Habitat dev environment uses Docker. So let's go ahead and build a Docker image of that service real fast, and then we'll use it again later. So we'll do hab package export Docker Atom Redis. So what's happening here is Habitat's installing Docker, right? Because we need it in order to actually build the artifact itself. So we're downloading Docker. And this is one of those moments where it takes a little longer than maybe I have to talk about. But one of the things we want to do with this feature is add more and more different kind of package formats. So I'm doing Docker here. We have ACI. We have Mesosphere. But we want to expand it, obviously, into things like AMIs, virtual machines. Like, you should be able to build whatever you want. So here what we're doing is we're installing, we're actually building our image now. So it's making sure we download the keys we need to validate the software. That's a thing we'll use later when we talk about update strategies. There you go. So now we built the image up, and we're shipping it off to Docker. And in a second, boop, we have a container, right? So that was awesome. What's great about that is that container only has the things that software needs to run, period. So all it has is Redis, glibc, the Habitat supervisor, which we'll talk about in a second, and the things the supervisor needs. So it's as minimal as we can make it. And we're going to work to make it more minimal over time. Okay, so before I move on, sort of a couple things I want to make sure we talk about. So one is these Habitat packages, when they're built this way, they'll run on any modern 64-bit Linux. So anything with a relatively recent kernel, I think it's 2.6.24. If it's newer than that, then the software that we build on it will run. The other thing is that Habitat gracefully supports proprietary software. So if you think about all the software that exists in the enterprise, it's cool to build things that can compile open source software and give you all these great benefits. But if you bought software off the shelf, you don't have the luxury of recompiling it. And so in this case, what Habitat does is you just wrap that software up, put it in an artifact, and you get all the management benefits, and you just lose some of the beautiful dependency stuff, right? So it scales elegantly from all that lovely dependency stuff into, yeah, you know, I don't know what the dependencies are, but I can tell you that it'll run if you install it on CentOS 6. Okay, let's run the package, right? So the next piece of Habitat is a supervisor. So we declared a service earlier, and now we want to run it. So we're just going to run hab start Atom Redis. So this is the package we built before. It's going to go out, it's going to download it from the depot, bloop, and then it started up. So the job of the supervisor is really to keep the service running and to manage it through its whole life cycle. So in this case, it just started it up and kept it running. And you can see, you know, there's a little bit of boilerplate, but mostly it just gets to business pretty fast. It configured Redis, and then it started it up. So one thing that's fun about Redis is that it gives you some warnings out of the box. And this is the sort of thing that if you were going to go deploy Redis from development to production, you would need to fix, right? You can't just leave those warnings floating around because eventually your operations people would be like, man, your software has a lot of warnings. So let's try to fix that. So what we're going to do is fix this setting here. So if we look up, there's this TCP backlog setting, and it helpfully told us what the right setting is. So it said the backlog was 511 now, and it needs to be 128. So let's go ahead and just set the backlog to 128, right? So Habitat provides a couple different ways to do this. So the first, and sort of least flexible but most portable, is you can just set it through the environment. So this is the equivalent of like the 12-factor applications, right? Anything that you can configure, you should be able to do through the environment itself. So, but the first question, if we back up even from that, is what exactly is configurable? What's the syntax I need to use to set that TCP backlog to its value? And so historically, what you would need to do is go Google for Redis, right? We would go Google Redis, we would look at the config file, we would find the thing, we would then have to figure out where that lives on disk or how it gets in the container. But with Habitat, we can just ask the supervisor that question because the automation, everything you need to know about the service lives with the app itself. So we're just going to say hab sup config atom Redis. What? Oh, I haven't installed it yet. Boop. Okay. There we go. So now that we have it on disk, we can get the configuration. And it tells us right here that there's a setting called TCP backlog, and it's 511. And what's neat about this is it'll work with any Habitat-enabled service. So if you have a Habitat package and it has anything that's user serviceable, you can just run hab sup config that package, and it will just tell you everything you can change. And since it supports comments, you can helpfully annotate why you would change them, and then you can stop having to Google all the time how to configure the service just because you wanted to know what it does. The service just tells you. So here, let's go ahead and we'll set TCP backlog. So we're going to do through the environment. So we'll say hab redis TCP backlog equals 128 hab start atom redis. Boop. So now you can see we had 3 warnings. Now we only have 2, right? So that backlog setting has been fixed. And that's awesome because it works everywhere. It sucks because you can't really change it once it's done. So once you deploy it, or once this happens, it's just sort of there, and it's externally enforced. And you have to figure out some other system. You have to tell something else to do it. And it sucks to have to do that. So let's get one little step better, because the environment can never, ever change. And let's just do it through a file. So another common problem you'll see is asking yourself the question, where does the configuration file for that service live, right? It's just a question we ask all the time. So Habitat makes that really easy too. So every time you run a Habitat package, what happens is we create a directory that looks like this. So hab service redis, right? So I'm just going to create it before I even start the package. And then we're just going to put a little bit of stuff inside there. So if you want to configure anything in Habitat, it goes whatever the name of that thing is, in this case Redis, and you can put a file called user.toml, right? And anything that goes in user.toml, that becomes your configuration file. So we'll just say TCP backlog equals 128 log level debug. We're going to add a little bit of log level debug because it makes the output of the demo. And now we're going to start. So we'll say hab start Atom Redis. Boop. And so now you got the debug output, and you have that TCP setting fixed. So what's great about this is that universal location, right? Anytime you get on a box and it's running Habitat services, and you go, where do I go to manually configure that service? The answer is user.toml inside the directory named after the service for every service for the rest of all time, which is pretty great. But it's still fundamentally externally enforced. And so we can do better than that. The next thing the Habitat supervisor does for you is the supervisors can communicate with each other. So far, we've just been running one supervisor managing the lifecycle of that one application. But the Habitat supervisors can join together, and they can form a ring where they communicate with each other into what are called service groups. So you can think about one instance of a service, Redis. But when you communicate, when you hook together the supervisors into a ring, they start to think in terms of service groups, right? So we have a service group now, and it's called redis.default. And we use a gossip layer to communicate the state of what's happening at each of those supervisors with each other. What's cool about that is that you don't have to deploy anything to get all of this behavior I'm going to show you here in a minute. It just happens as you deploy the applications and wire them together. It also increases your availability of the management layer as you scale out. So as you deploy more applications with Habitat, the availability of your management layer also goes up, which is neat. So let's go ahead and configure this service through the ring. So we're going to start another instance here. So here's Atom Redis. While that's going, we're going to pop over here, start another terminal window, and we're just going to do one more time, TCP backlog equals 128, log level equals debug. So now we're going to run hab config apply. So config apply is going to take that config file, and we're saying, hey, this is the configuration for the Redis default group, and we're going to set its version it's the first time we've done it, so it's the first version. And here's the data, and then we're going to pass it a peer. And so in this case, our peer is this guy right over here. And we're just going to send him our config. Boop. And so if you notice that other terminal window, we applied that configuration. He recognized it. He reconfigured the service, and now it's running the right way. Where this becomes awesome, though, is what happens when we start another one. So when we say start Atom Redis over here, we can pass that same option to Habitat, and all of a sudden, this new one is also correctly configured, right? And what's awesome about that is we didn't deploy anything, right? We didn't have to go out. There's no like magic service discovery software that hides behind this, right? It's just the supervisor doing its thing, because the automation has to travel with the application. Every single problem you encounter in that application's lifecycle over time has to be the application's problem. And so in this case, the supervisor takes care of managing the right configuration for the right service, right? And it just does it for you by deploying the service, right? Okay, so the supervisors can do more. So fundamentally, that configuration trick is awesome, but it's still pretty static, right? And there's really two classes of dynamic configuration you have to worry about. So one is topologies. So that is orchestrating a service within that service group's own boundary, right? So not all services need a topology, but many do. And so one example for databases that's really common is the leader-follower topology, where you have one database where all the writes go, right, and most of your reads, and then you have followers that you sort of stream the data to as things come through. And Habitat talks about those topologies at the service group level. So you specify when you start the service what topology it should be in, and then the group joins together. And we use the ring to actually dynamically configure those services. And there's a bunch of different topologies. We hope to build more. So two that are there now, one is leader-follower, which I'm going to show you now. Another is initializer, where an example would be one node has to come all the way up, and then other nodes can join it, right? And then the default you've been seeing is just standing alone. So let's go ahead and do a little bit of leader-follower. So I'm just going to pop open a couple more windows over here. All right, so let's start this guy up. So we'll say have start Atom Redis topology leader. And so what's cool here is all I did to get this dynamic service discovery and this dynamic topology is I just passed a flag to Habitat, right? We kept it as simple as we could. So we'll start this guy up. He installs the service. And what we're going to do now is block. And so the reason we're doing this is that it's not safe to actually elect yourself the leader if you're alone, because there's no difference between being alone and being net split from a working cluster, right? So we require a quorum of 3. So until I start 3 nodes, the supervisor won't actually bother trying to start the service. So let's go ahead and start another one. Topology leader. And this time we're going to give it a peer of the other service over there. And while that's running, we'll do this one too. Okay, so there's 2. Here comes 3. They noticed they had quorum, and now they elected a leader. And I think the leader is this guy. So this guy right here got elected the leader. The other 2 automatically configure themselves to be followers. And if we shoot the leader, if we just kill the leader right now, it's going to take a second. One thing we lost in the beautiful future of cloud-enabled infrastructure is the ability to just plug a cable in between 2 servers and be like, hey, are you still alive? And if it's not, like, shoot it in the face. So it takes a minute longer to do things like failover. So the supervisors right now are checking to see if each other are alive, and they're going through this cycle to decide that that peer has gone away. And once they notice he's gone away, they're going to use these 2 who still have a quorum to elect themselves a new leader. And it should happen any second now. This is always high tension, but it always works. Come on, guys. You know you want it. There we go. Okay, and they elected a new leader. So now, we've successfully transitioned in a topology from a working leader to another working leader. And all that stuff happened without deploying anything else. So just to point on it again, the application traveled with the app, right? All that intelligence on leader-follower, on being able to decide what's what, that all just happened because we ran the supervisor and we pointed them together. The other thing that's great is that the data is the API. So if you look at what we had to do, we didn't make any changes at all to Redis to make this happen. It's not like a patched version of Redis. All we did was take more data from the supervisor and used it in the configuration. So in this case, it's just these couple lines right here where it says, if I'm a follower, make me a slave of the IP address and port of the leader, right? And that's a really great pattern in Habitat. So any application that's inside of it, really, the supervisor just keeps feeding more and more data. And either you read that data directly, if you were written for Habitat natively, or you use templates to get it into your application to do the right thing. And all sorts of data is inside this API. So it tells you about your topology, it tells you about what services are running, what other things are available. It has the package information, all kinds of stuff. Okay, so the other kind of dynamic configuration is service discovery. And so this time, we're going to do, instead of doing Redis, because it's kind of boring now, because you've seen it happen a lot, we're going to do Postgres and Rails. So I happen to have some configuration already pre-baked that's just setting some usernames and passwords. So we're going to use the ring to do that. So we're going to have config apply PostgreSQL.default. It's the first time. And we're going to do this Postgres.toml. Oh, wait, I need a peer. I even had someone holding up the thing I have to type, and I forgot to do it. 0, 2. OK, so there's Postgres. So now we're going to do template databases. So that all happened in the initialization hook, and now the service is up and running. So over here, we're going to start our Rails app. So we'll say hab start core Ruby Rails sample. Peer is 172.17.02. And then we're going to pass another option, which is called bind. And so our Rails app takes a data structure called database. It just needs a database, right? And so we're going to say database PostgreSQL.default, right? And so what's going to happen when we fire this up is it's going to download Rails and all of its dependencies, which again, turns out it's a lot of stuff. And once it's done, it's going to reach out to that ring. It's going to take that config that we applied earlier that's just waiting for the service to come up, right? It's just sitting in the ring doing nothing until a service comes along that says it needs it, right? Which is about to launch in just a few seconds. And what's going to happen is it's going to automatically bind itself to that Postgres database we built earlier, giving you automated service discovery. Here we go. There's Perl. And Postgres itself, because we have to link to Postgres. We're almost done. Here comes Ruby. And sed. Oh, now we got our application. So you don't even think about it normally, but now you're like, wow, really? You need sed? Weird. OK, here we go. There we go. So now the supervisor started. He grabbed his configuration. We're linking in that database because we did discovery. So if you saw up here, one thing that we did was, in that initialization hook, we ran our migrations, right? Which is a pretty common strategy for Rails. And that migration actually created the database that we connected to over discovery and then started up the app. So if we want to go see this guy, let's go look, because what's a demonstration without proving it? So if we go here, we can pop up a terminal window. And we'll keep it old school. Oh, no. What you talking about? All right, I won't do it. Look, trust me. No, we'll do it even more old school. Bam. What's up? The important part here is the data itself is the API. The supervisor can do some more things for you, but we're gonna smooth past a few of them. So one is update strategies. So this is some functionality that allows you to take software that's in that depot, and if you add the strategy flag to the supervisor, it'll watch to see if a new version becomes available. And if it is, it'll orchestrate downloading that software and upgrading itself and making sure that it's healthy. And so some topologies, some examples of topologies of update strategies we want to have are all at once, so just update as soon as you can. Others are like one at a time deployment, right, where I want to be able to just say deploy to one box, then the next, make sure they're all safe. Another would be progressive, right, deploy to one server, then two, then four, then eight, right? And these strategies overlap with being aware of their own topology. So if you run an update strategy in a leader-follower cluster, it'll update the followers first and then the leader last. And this is really ideal for continuous delivery, because if you think about the things you need to say, one is the topology of the service where I deploy it. The other is, how do I update that service safely? And all that stuff just runs with Habitat and lives, again, with the application. Not all the software in the world lives in Habitat, and so Habitat also provides a REST API that allows you to check on things like the health and status. And this is great for integrating with things like load balancers or other external services. It also lets you debug the supervisor itself. So Habitat provides application automation. It thinks about the world from the application's point of view rather than the infrastructure. And when we use Habitat, the automation travels with the app. All of its behavior travels with the application, and the only thing you need to do in order to get the application to work is deploy the application. That's it, and just add a couple extra options. And it works great for existing software that just gets wrapped up by Habitat. It also works great for new software you want to write specifically to Habitat that runs on top of PaaS platforms or containers or any other thing that you need to do. And the important thing to remember is you shouldn't have to change what infrastructure your application runs on just to get better management, right? You should be able to just have the application be easy to manage, and that's what Habitat gives you, right? It moves that management problem into the application's domain and says, hey, let's just solve it here. The application will handle all of its management, and now the only question you need to ask yourself is, what's the right platform to run it on? If the right place to run my app is in a data center with a SAN, I'm going to run it in a data center with a SAN, but I want to manage it the same way that I manage my amazing applications running on Cloud Foundry that do all this auto-scaling and shenanigans. And it shouldn't be different, and with Habitat, it's not. And ultimately, that allows us to form better teams. What we're all looking to do is be these modern application teams that work together to ship software fast and to make sure that we can really become those fast, efficient, software-driven organizations. And Habitat does that by allowing you to simplify the process by which you take an application through its lifecycle. It allows you to empower that team to work closer together, because as we talk about the application's lifecycle, we're just talking about things like topologies, and update strategies, and configuration application, right? And that's way easier than having to talk about all the infrastructure components that get you to that place, right? And then last, it accelerates the rate at which those teams can work together, because they don't have to think as much about the management layer, and they don't have to think about all the infrastructure that goes with it, and so they can go faster to get that software out into production because they avoid that production cliff. And that's what enables them to really become the fast, efficient, and innovative software-driven organizations that Chef hopes we can help empower everybody to be. And you can get Habitat today. It's available right now, www.habitat.sh, and you can have it all. But we're not done. There's one more thing. It's all open source. So Chef is an open source company. That's our roots. That's where we come from. And we believe that if you're building foundational software that's going to run the heart of everybody throughout the world, that software has to be open source. People have to be able to look at it. They have to be able to read it. They have to be able to fix bugs. They have to be able to make it their own. And they have to be able to rely on it as a core part of what they do. And so even the website is open source, and you can send pull requests against all of it. And the software that we build in Habitat is all open source, and will keep being so under the Apache license. If you're an existing Chef customer, I have good news. You have support for Habitat. So if you decide you want to go use Habitat, come engage with us in our open source community. And if you decide you want to put that stuff into production, we're going to back you up right now the same way we back you up with Chef. But we have a lot more to do. In the next coming weeks, we're going to launch an automated public build service that will take those plans from like a GitHub repository, automatically build the software for you in a studio, and then host it in the depot, so you don't even have to bother with that part of the setup. We want to add more topologies, more update strategies, more plans, more package export formats. There's a ton of stuff we want to do, and we can't wait to do it with you in the Habitat community. So go check out Habitat. It's at www.habitat.sh. You can hear more at ChefConf in Austin. We're going to have lots of conversations about Habitat there. That's July 11th through the 13th. You should definitely come. There's going to be an awesome show with sweet bands. I'm going to be in Salt Lake City talking at Salt Lake City DevOps Days tomorrow, along with Jamie Windsor and Fletcher Nickel, who helped build the system. And if you're a Chef person, you should know their names because they're amazing. And so you can come and hear more. Thank you so much for watching, and I hope you love Habitat as much as we do. Thanks. Thank you.